All right, let me share my screen. Can everyone see my screen?
Yep.
All right, so welcome everyone to lesson 5. Excited to be teaching today. So we're gonna start off with something a little different today. We're actually gonna look at some Python code. Here on the right, I have some Python code. It's most of you might have seen it, some of you might not have, that's totally fine, but can anyone guess what's wrong with this code?
Adding an integer string.
So sorry.
Adding an integer in a string.
Yep, that's right. So obviously adding 5 plus the word cat is weird, right? But the interesting thing with Python is that if I open it up here and I try to run this code, press enter, and then I do my fun, let's say 11. So what do you folks think is going to happen if I press enter here in Python world?
Return hello.
Yep, exactly. So it's going to return hello. It says, Python says, if I go down this branch, I don't even know about the existence of this branch. I haven't even seen this bug yet, so I don't care. This branch is fine. I'm going to return hello, and the code is going to seem like it's working. But if I do 9, then I get the bug. So that's kind of interesting, right? And you guys have spent all this time learning Hoon. This might be kind of horrifying or troubling to you, right? And as you know, Hoon is different. This is kind of the corresponding gate you might have if you're trying to do this thing. And if you try to type this in, like, okay, let's get out of Python world and back to Herbit world. So if I type this in, like it's just immediately gonna say like, hey, like you can't do that, right? So we're hitting upon a very important difference here between two different kinds of programming languages. So there's this thing called statically typed languages like Hoon and dynamically typed languages like Python. So statically typed languages will check all of your types, all the conditions, all the types, and how they fit when you compile it, when you go to build your code. And obviously this has an advantage because you can find these errors when you're building it rather than, oh, when the user runs it and something breaks, right? And that kind of stuff can happen in Python. However, the trade-off is when you're coding in a statically typed language like Hoon, you have to be much more careful and explicit with your types. So that's kind of the trade-off there. Does that make sense to everybody? Awesome. Yep, exactly. When it compiles, it's mostly correct. All right. So what are some ways that we can work with this statically typed system, kind of be more explicit with our types, give it more information, and just encounter less typing bugs? So something you guys have already seen is the use of kethep, right? This is some pretty simple code. We've seen stuff like this before. We have a gate, and you take a number, we add 5 to it, and this kethep here is ensuring that the output is also a PAT-UD, right? So that's it's useful to sprinkle these throughout your code. Something you may or may not have seen is the related cat-lus. So do you folks want to look at this code and tell me what it might be doing? So it's taking a list of atoms and a list of ships, and it's welding those two together. And then what is this cat-lus line doing? to that result of the weld.
It's a fence, I'm assuming also where only lists of PAT-Ps can go through.
Yep, exactly. So it's fencing this code saying, I want this to be the type of ship list. So in particular, we're not giving it a type here, we're giving it a noun, right? And it's inferring the type of this noun, and then it's casting with that inferred type. So it's basically just going to make this return a list of PAT-Ps, as you said. All right.
And how is it different than ket-hep?
Yeah, so if we go back to ket-hep, see, we gave it a type, right? We gave it an aura of PAT-UD, whereas here, ship list is not a type, it's actually the name of a noun that we passed into the gate, right? Does that make sense to everybody? Yeah, so that's useful sometimes, like just cast something to the type of this other thing. It could save you some code. Yeah, cast by example. A sum type. Sorry, what do you mean by sum type?
Sorry, is like the whole point of doing that? Say, well, I guess in your example, ship list is only of one type. I was thinking like you give it by example because ship list could be like, it could be either one type or another, and you just want to be able to handle whichever that type is, but it doesn't.
Oh yeah. Like if ship list was a type union, like a custom type union, exactly. You can do that. I didn't say anything wrong, Neil, right?
Yeah, I see this most commonly when people are working in the kernel or doing complicated things with cores, and they've got an example of something and you don't really want to remember exactly what it was. You have this thing that's big and complicated and messy. You just want to say, like, give me back something that's the same shape as what I have. Now, what is interesting is if you go dig around in the docs, you will find that ket-hep, which you are probably thinking of as more fundamental right now, ket-hep actually is sugar for ket-less of the bunt of the type.
Yeah, that's an interesting factoid. So I guess this one's more fundamental. But yeah, like Neil said, like if ship list was actually some insanely complicated thing, like the state of an agent or the state of like your whole orbit or what stuff like that, like it's much easier to just use a ket list than like try and actually figure out what the whole type is. It might be some huge thing that's impossible to type. All right, moving on. So here we have two new runes. So what gar asserts that the next thing must be true, otherwise it'll crash, and what gal asserts that it must be false, otherwise it will crash. So these are also useful to pepper throughout your code. We're just saying, like, make sure this sanity check is true, otherwise your code should crash and like not continue onwards. So here's an example of the gate. So can you folks figure out what this gate is doing? So we take a TAS as input, we're returning a tape, and here we have a custom type definition. So we define our type as a type union of send crow, send jay, send pigeon, send swallow. And then what are we doing? What are we doing here? Yes, we assert that the animal is a bird. So if we have this code, yes, otherwise crash. So if we have this code, so if I call this my gate, and then I type this, and then I could do my gate send crow, it'll say your animal is a bird. And if I do send cow, I'll get dojo Hoon expression failed. And that's coming from this wakar. this assertion right here. Yes, that's an interesting challenge. So moving on, or are there any questions on this? Okay, no questions, then moving on. Here's something you've seen before in, I think, 2 lessons ago. So you can also use this what null as an assertion. And this is actually telling something to Hoon's type system, right? Because if you recall, like if we have a list here and we assert that the list is not null, then we can grab the head of the list. But if we don't assert that the list is non-null, then we can't do that. So this is something that's kind of similar to these runes, but it's particularly asserting that something is null or is not null. Okay, so are there any questions on any of the stuff above? Yes, I dot something is like I dot a list is the way you access the head of a list, but you can only use it if you have a check beforehand that the list is non-null. So the compiler will only let you use that if it knows the list is not just a sig. Yep, and tail is t dot my list. Yeah. All right. So so we're if there's no more questions, I'm going to move on. Something interesting about auras. Actually, I just learned this, but auras nest character-wise. So pat t nests under a pat because like pat fits within pat t, right? But also pat ta nests under pat t because pat t fits into pat ta, and same with pat tas. So that's kind of an interesting feature about Hoon's aura system. So in particular, we can do all of these castings here are totally fine. So like you can turn a TAS into a pat T, TAS to a TA, and we can even turn a pat T into a pat TAS, go the other way. But you cannot turn a pat TAS into a pat U because TAS or U does not nest into TAS, right? Just alphabetically. And something interesting is you can even do custom auras. So you can do like I just made this aura T custom, and you can like nest that under T. But you can't nest T custom under TAS because T custom doesn't nest under like alphabetically under TAS. So that's just like a cool little feature. There's not too many reasons you'd normally like use a custom aura, but Neil tells me that they're useful sometimes. So yeah, any questions on that?
Does it necessarily have to like start with TA?
Oh no, I was just using like the T something series of auras because that's like a nice, it can be any, yeah, as long as the alphabetical nesting is there. So
No, I mean like T custom, we had to put the T so that it nests under pat T's, right?
yes, exactly.
Yeah. Okay. See. Yeah. Thank
Mhm.
you.
This is more that you will run into nesting rules like pat UD and pat UX do not nest inside of each other, but they do both nest inside of pat U and pat, which is the raw atom. It will be, you will probably never write a custom atom aura in your life unless
Oh.
you get the kernel work, but you could. The rules apply.
All right. So moving on then. So last week we had a big lesson, right? We learned that cores are the big pattern in Hoon. And this week we're going to learn some more about how to use cores, how to work with them. So if you're in a core, something you might want to do is make a custom type definition, right? And the way you do this is with the lustbuck arm. So if you recall, like usually for values, like just declaring a value or like making a gate or something, you'd use lust. But to make a custom type, you want to use lustbuck. So here, we just said in this core, we're going to have a type called URL, and it's going to be a pat-t. This is pretty simple. Like URL doesn't have any special properties other than being a pat-t, but like for your own convenience, for your own like memory, when you're like writing code, it's useful to do stuff like this. Like you can cast something to a URL, etc. And here's something a little more complex. So we're making a custom type called ship. And here we're using the type union, which hopefully you guys are familiar with now. So we're saying a ship is a custom type, which is either a send galaxy, send star, or send planet. So that's pretty straightforward, right? Any questions on that? All right, so what's wrong with this code? This code here. What is wrong with this? Can anyone tell me?
Oh, this is subtle.
Yeah, no worries if you don't know. I'll explain shortly, but I'm curious if anyone has a guess. Okay, so
Is it the hyphens?
sorry,
Is it the hyphens?
the hyphen right here.
No, the 2 number cell hyphens.
Oh no, yeah, this is a totally valid definition of a face. So
Okay. I tried.
nice guess though, nice try. So we're gonna introduce something new here. So not exactly, Rashid. So oh yes, so you can define redundant types. That's totally okay in Hoon. So that's not the issue, but good guess. So the issue here, okay, so Hoon actually has 2 modes. So usually regularly when you're coding, you're going to be working in what's called value mode. So value mode is like saying just like send or call hep like 1, 2. Like that's value mode, right? We have 2 values, 1 and 2, and we're making it into a cell. But there's also a different mode, which is like a higher like meta level mode called structure mode. And when you're in structure mode, you're talking about types and structures. So you're not talking about the actual values. You're talking about like structures which can contain values. And when you're defining something with lustbuck, you are in structure mode. You're talking about structures, and you're not talking about the actual values contained in the structures. So this rune right here, col hep, is the wrong rune. So that's the issue here. Col hep is a value mode rune that is used for actual values like 1, 2, or like send A, send B. Those are all totally fine for col hep, but not talking about types. Okay, so how do we fix this code? This is the right way to do it. The first one is going to be the second one is going to be the more common way you'll see it, but these are equivalent. This is sugar for that one. So you got to use this rune, the buck col, which is forming a cell type, right? If you remember that. So the possibly confusing part here is that when you're in structure mode and you have a buck call rune, that sugars to like this cell notation, right? And when you're in value mode and you have like a Colhap rune or other Col runes, that also sugars to this cell notation. So you might get confused a little when you see the cell, but just remember that like there's two modes. That's a good question, Rashid. I don't think it is. Let's try it. So yeah, that looks like that does not work. I assume you meant to put the buck colon in front of the parentheses. But I think if you do like this, yeah, that works because terms are types. So this works, but it's because these are interpreted as types, but 1 and 2 are not types. So this is not going to work. That makes sense.
Actually, small alteration there. Sen1, %1 and %2 are constants, not terms. Term stuff actually gets really complicated, and there's a lot of things that are constants that are not terms and vice versa. We can kind of gloss over that at the Hoon school level, but technically these are constants, but they do serve as an instance of the type of the value as the constant.
Okay, so I use some wrong terminology, but the point remains. If you put the sens, these are types, so that's okay. We're in structure mode with this rune, but you can't do this because these are values and Buckle expects types. Okay.
Although I think what might be happening here
Yeah.
is that it's trying to I think the parser here might be trying to resolve buck against the subject. No, this will be parsed. Actually, can you zap comment real quick?
Like that. Like that.
Zapcom pal. No, Zapcom takes Tarhoon as the type.
Sorry, so what do I do?
So Zapcom Tarhoon.
Oh, so tar this.
Zapcom open parenthesis,
Oh.
then Tarhoon,
Oh, okay.
and then ace, and then par. Yeah.
Okay.
Okay, so this is. Yeah, this is actually trying to resolve. This is a weird one. This is a weird one because it's trying to resolve buck as a wing name against a subject that is attempting to evaluate one as if it were a gate against a sample of 2.
Huh.
So it's kind of like, unfortunately, it's like a pathologically complicated example for Hoon School. we can go through and explain every part of what's going on here. And maybe it's worth pausing and going back to it later on, but we could definitely waste a lot of time trying to parse why this particular example is failing here. It doesn't work, but it is failing for an interesting reason. And it's partly because it's not actually hitting the buck Col rune.
Huh. Okay, well, in the interest of getting to all the content in this lesson, we'll have to move on, but are there any more questions on this section, structure mode and value mode and all that? All
Can
right.
you quickly summarize the rules of how you know you're in which mode? I'm not sure if you commented on that.
Basically, it depends on the runes you're using. Like this rune, like buck something says I'm now going to create a type, and then that puts you in like structure mode for the children of that rune. And yeah, maybe Neil has a better way to phrase this.
Well, the short way is if you are if you are writing a sample specification in a gate or a door, then you're in structure mode. And otherwise, you're in value mode unless you're doing something weird, which you almost never are.
Like, yeah, but like you're writing a gate and you're here, this is structure mode. Or if you're doing a less buck, right? That and then you're also in structure mode. And then
Yeah, and type constructor arms too, yes.
yeah, and all the other time you're in value mode, basically. Any more questions on that? All right, moving on. So let's learn a little more about working with doors. So if you'll recall, doors are cores with a sample, and a sample is just input data, right? So we've learned kind of like two ways to evaluate like deferred expressions, like functions, right, in Hoon. So the first one is pretty straightforward stuff. We learn how to use a gate. Like this gate takes a number and just adds 5 to it, right? And if we put that in our dojo, and then we can call it with send hep add 5 1, right? And that gets us 6, or we can call it with a sugar syntax, right? That gets us 6. So pretty straightforward stuff, right? Then the next way we learn to evaluate deferred expressions is with a door, right? So suppose we have this code here for a door. What's going on? It takes a sample, which is n, and it's a pat ud, and it has 4 arms, and this arm just adds 5 to it. This arm subtracts 5 from it, and so on, right? And let's go through how we might use this door in our dojo. So let's call this my door and paste it in here. And this is the syntax we'll use, right? Maybe you folks remember this, but we use this rune called send sig. The first argument to send sig is going to be the arm. The second argument is going to be the door. And the third argument is going to be the sample for the door, right? So just do this. So, and these are all equivalent. These are just different ways of sugaring it. Right, so then we just multiply 2 by 5, yay. And we can also do, this is the syntax that you'll encounter most often. So we got 10. All right. So now I'm going to tell you something interesting. So here we had a gate, right? And here we have a door. They look like different things, but actually this gate, and calling the gate with the send is actually just a special case of a door, and calling it with a send sig. Can anyone tell me why that might be the case? Does anyone have a clue about that? So this, I'm saying this is a special case of something like this.
Is it just a one-armed door?
Exactly. Yep. Very good. So if we have this gate, right? N equals UD, add N5, we can write this gate as a door exactly this way. So here we have a door with a sample. It has one arm. It's just the default arm called buck. And then we're in that arm, we're just doing the same thing here. So the way you call it, so in that case, this send sig buck my door 1 is equivalent to send hep my gate 1. And I believe like Hoon actually in Hoon, like this is actually a sugar over something like this, right?
So then what's the difference between a sensig and a senhep? Like why use different calls? Calling
Yeah,
them.
so like gate is like a common pattern, right? Just there's not like multiple arms, right? There's just one thing and it takes one kind of sample and we want to evaluate a certain way. And that's like a pattern we use a lot, right? So you wouldn't want to always be like, oh, I want to make a gate, so I have to write the door and I have to write the arm and the default buck arm and all that. So this is like a helpful pattern for us. That's what a lot of things in Hoons are in Hoon are like helpful patterns that are like simplifications of other things. If that makes sense. Any more questions on this? So the difference between senhep and sensig. So yeah, senhep is when you're calling a gate, and a gate, in like the details of it, a gate is a door with a default buck arm. But when you're writing a gate, it's actually going to look like this. And so when you use senhep, it has to refer to something with this room, basically the bar tis, something that's a gate. And whereas sensig has to refer to a door, a core with a sample and some amount of arms.
This is a little off topic, but you know how like runes, the first character in the rune sort of gives it a function type. Is there a similar thing where the second character in a rune kind of you can infer something about that rune based on that second one, or is it just more or less random?
Yeah, that's a good question. Maybe Neil knows. If it isn't that way, I feel like it should be that way because that would be very, very good, right?
Not really.
Okay.
There are some subtle things like buck coal does make cells, but in general, the second character, I mean, so if it encodes semantic information, it's not along a pattern that carries across families. So for instance, if you're doing if you're looking at like an and or an or operation with a buck character, then buck bar is or, which is pattern matches with the way that or is used in C, C++, and other languages like that. Buck Pam, buck ampersand is and for the same reason. But that wouldn't carry across other families.
Yeah, I think it'd be really nice and elegant if they could do that, but I think the issue is that like within these different families like bucks and whatever, like there's not enough like analogous stuff. Like it's not like every function in this family would also have an analog in that family, you know, so yeah. But good question. Yeah. Good stuff to be thinking about. All right, so if there's no more questions on that, I'll be moving on. So let's talk about maps and sets. So we're going to learn some new data structures and in the process, gain some more experience on using doors in practice. Most of you are probably familiar with what a map is or a dictionary. And if you aren't, that's totally fine. So basically it's a data structure that contains key value pairs. So, and here we have a key, which is Mazda, and value, which is RX-8, so a type of a Mazda car, and etc. Right? So you can imagine there's like a lot of different uses in programming that you'd want to use a map, right? Pairs of keys and values. So let's gain some practice with using maps in Hoon. So well, it's quite small, but hopefully you guys can see it. This is how we are going to make a map in Hoon. So we have this function called my right here, and that is going to take these boy examples don't work for me. Sorry, what boy examples?
I don't know that a Mazda correlates to
Oh,
X.
oh, I'm sorry. Oh, I was like, wait, what?
I was
What
just
boy?
joking. Cars.
Yes, yes. Uh, but yes, so back to the colors map. So we have this function my, which is going to take a list of pairs, and it's going to put that into a map. And here we're just doing a cast to make sure that the Hoon compiler knows what this is. So if I type this in to my dojo, and then I do colors, then it's going to tell me that it's a structure with a bunch of pairs, yellow and the hexadecimal for yellow, blue and the hexadecimal for blue, and red and the hexadecimal for red. So that's pretty straightforward, right? The important concept here is we're using this my. That's how we're making this map.
My is the keyword in the standard library.
Yeah,
I see. All right.
yeah. Maybe Neil has something more to say about this.
Sorry, what was the question?
Oh, I just like about using this my to make a map.
Oh, I was just making sure my was, I didn't know if that was like a like one that Jack defined, or the thing is literally called my. But okay.
No, it's the map builder. It
Yeah.
takes a list of pairs.
Okay. So suppose we have this map that we made and we want to put something in it, right? So now we're going to get a good example of using a door. Okay. So to work with maps, there's a door called by, and it has a bunch of arms that contain various different functions. And we can think of by as the thing that contains the map library. So we have this code here. We have a sensig, and sensig takes as argument a arm name, a door name, and a sample for the door, right? So when we call this, what we're actually going to get back is a gate. So this doesn't return a map. This returns a gate. And what that gate lets us do is that gate then takes as input a key value pair and then returns a new map. So if we look at this code here, we have this sig put by colors, which is what we saw in the last slide, right? That is the gate. And when we call that gate on this cell of green and a hexadecimal, then this whole thing is going to give us back the new map with the new value in it. So there's a lot going on here. I just wanted to check and make sure people follow what's going on and see if there's any questions.
I have a quick side question. I think that something I've been pondering for a long time. I know semantically this will work like classic maps in other languages. I'm guessing because fundamentally underneath it, it's still a tree. Would I be correct in thinking that the performance characteristics will be more like log n rather than O1 in terms of performance? Because everything is fundamentally a tree under the covers.
Yeah, that's a good question. I would guess so, yes, but I don't know, maybe Neil has something to add.
Or can jets be fancy enough that it can change how it stores it in such ways that it can have more effective performance behavior?
Are there map jets? There must be.
I mean, I'm
At least-
sure they're jetted. The question is can you get around the fundamental tree data structure that everything is represented by performance wise.
I think
Or not.
everything's log n.
Yeah,
There's a few places like lists are just less efficient, like tapes are just less efficient than chords because they're linked lists
yeah.
in the C representation. I really think that this is probably not something that they have remotely optimized at this point because it hasn't been a blocking speed concern.
Are
Yeah,
jets
sure.
flexible enough that you could, in fact, now that I know it's a map, I can essentially represent it by a different data structure as long as the behavior is semantically
Well,
precise?
when you build a jet, you do have to assume, just by the nature of knock and the way it pulls in the context at the moment of execution, right? So the payload is the sample in the context, and the context is handed in to the jet as well. So the jet dashboard is not maintaining separate state that's monitoring everything that's going on in your system. So it's not like there's a different, more efficient map that is
Yeah.
tracking what's going on in your
It's-
knock, in your, in the actual Arvo.
So
So
I hate
what would
it.
happen is if you're going to run something in a jet that needs to be ran efficiently, you'll have to do a conversion in C from the knock representation into whatever you want to do fast in C, do what you're going to do in C, and then convert it back out. And so it's kind of like
Yeah.
GPU programming, right? Like you have to decide whether or not the cost of doing that conversion merits the speed up that you would get by doing that transformation. And I don't know where they've ended up on this question, or if it's really been visited in this case.
Okay,
So this is a fantastic question for either Hooniverse or battery payload. So someone like Master Morzad can jump in and give you all the details. For the interest of time, gotta keep moving on the lesson, but if you're curious, please do post about that somewhere. So is everyone following the usage pattern here of how we're putting a new entry in our map? So to refresh, here we're creating a gate, and we're creating that gate by feeding an arm in the standard map library, and our map, and this gives us a gate. And then we're using the gate by feeding it a pair of things that get put into the map, and this whole thing creates a new map. So is that pattern understandable to everybody? All right, great. So this is, I needed to belabor this because this is a super important pattern. We're going to be using it a lot. So, all right. So when we update our colors map, we don't actually like replace the original thing with a new thing. We actually just make a copy of it, and the new copy of the map has the updated stuff put into it, but the original one's still there. So for example, I could do this. So if you look at this code right here, I'm saying color 1 is my original map. I'm calling colors 2 is the result of putting orange into colors 1, and then colors 3 is the result of putting violet into colors 2. And then if I put colors 3 at the end, I get the map with all the stuff in it, right? And obviously I could do this, but except I could always call colors 1, right? And then that would get me the original map with just 3 colors in it, right? That's pretty straightforward, right? But when you're actually like working with these maps and putting stuff into them, you probably wouldn't like repeatedly name it different things. So in practice, something you might do when actually working with a map might look like this, right? So first we're saying we're defining our map colors with red, yellow, blue in it. Then we're just saying colors is putting by colors orange. So this is like this is the same name, but it's now we're getting a new thing, right? And here again, it's the same name colors. We're getting a new thing that actually has everything in it. So few colors, then we get the map. Yeah, so right, it's like an update, but the point. So give you a moment. I'll get to your question. So if I do colors here, we'll get the map with all the colors we put into it, right? But here's the interesting thing. So this old colors and this old colors are all still there. They all still exist in the Hoon's memory tree. So if I do this code, and then I do ket colors, that's one ket colors is going to give me the map with yellow, blue, red, orange, but not violet. So if I do ket colors, I actually can still get this colors right here before I put the violet in it. And if I do ket colors, then I can get the original definition of colors, which doesn't have orange or violet put in it. So it's all still there. Yeah, so hopefully that kind of answered your question, Rashid. Yeah, did that make sense, everyone? Okay, awesome. All right, so let's go over some more things you can do with maps. So has by colors. So same pattern here. We can check if the colors has teal. So there's no teal in our colors map, but there is red in our colors map. If we can get a list of all the keys in a map. So this is a little different than before, because here this sig key by colors, before this was a gate, right? And then you need to feed something to this. But in this case, this is actually just the final result. So you didn't need to feed anything else to this. And so something else that we might want to do in a map, pretty straightforward, is like, if we have a key, what's the value for that, right? So that then you can use get. So if I do get by colors blue, what's going on? Oh, I have a syntax error here. That's my bad. Wait. Oh, there we go. Okay, so if I do get by colors blue, it's gonna give me this, and this is kind of interesting, right? And if I get by colors brown, so brown is not in my map. So what's that gonna give me? It's gonna give me this. So, does anyone kind of have any guess as to what's going on here? If no, that's totally cool. I will explain. Yes, brown is not in map. But when I did blue, when I asked for blue, it didn't just give me the hexadecimal. It gave me a cell of a sig and a hexadecimal, right? That's kind of interesting, right? So what's going on here is we're introduced to a new data structure called unit. And a unit is either a sig or a cell of a sig and some noun. And the reason we have this is just a sig is equivalent to 0. Okay, so you can't return a sig and say, oh, that represents nothing is here. Actually, that's saying, sig is saying there's something here, but it's a 0, right? So we need a way to distinguish actually nothing is here or something is here and it's this, right? So that's what unit does. And yeah, So how we make a unit is using the following, any of the following syntax. So you can just manually construct a cell of sig and some noun, or you can use a single tick, and that does the same thing. Or you can use sum, and that does the same thing. And in particular, when you use sum, it actually like formally casts it to a unit. And so what if we want to grab the actual value out of a unit? Like, so suppose we did this get and we got this cell, but we actually need to grab this hexadecimal value, right? So we can do we can use need. And what need does, if you feed it a sig, is gonna fail. So yeah. All right, so I have a challenge question for everyone. Suppose I defined my map and I had some code here, just defined a map, right? And then I ran get by my map with some key, and it gave me back this. What does this mean? What does it mean that I got this? No, yeah, so that's the subtle thing. Yeah. So recall, yes, Bantus Follis, the value is a null, yes. So in this case, what this means is actually there was something in my key. My key had a value, and the value of my key was sig. So right, that's a tricky thing. And if you remember, if we go to our colors example, what happens when we look for something that actually wasn't there? It just returned a sig. Whereas the difference here is a cell of sig that's saying there was something there and it was a sig. All right, that makes sense to everyone? Okay, so we're close to the end. So another useful function when working with maps is called bind. So what bind does is if you have a gate, like say this gate here, right? It just takes the n, which is a number, and it adds 1 to n, right? We call it add 1. If you run bind on that with a unit as an input, it lets you feed a unit to this gate, which doesn't usually take a unit, and makes the gate also return a unit. So that's kind of interesting, right? That's if you want to translate from things in units and regular values, that's kind of useful. All right, so another useful data structure is called sets. So far we've been working a lot with lists, right? Lists look like this. What are some properties of a list? They have an order, right? They have a 0th index, first index, etc., right? If I want to grab the 0th index, I can do that. And there's no problem with repeating these values. Like there can be 2 1s or 2 3s, whatever, right? So sets are kind of like lists, but there's 2 key differences. Sets can only contain each unique value once, and sets don't have an order. So we can work with sets. We can make a set with the sy function, just like this. And there is our set. And putting things in a set is pretty similar to what we saw with the maps. So instead of by, there's in. That's going to be the library for set functions. And we can put numbers in. and see that they went in. There's a lot more set functions that I wanted to cover, but I think for the sake of time, I will skip these. All right. So let's go over some code. So here's some code. We'll save it as gen Caesar.hoon. And I will drop a link to a paste bin so you can look at it yourself and run it as well. There's a chat. There's the paste bin for you. So what does this code do? It implements a very simple cryptographic cipher. And the cipher is, we're just going to take all the letters in your message and just shift them. So like A becomes B, B becomes C, or you can shift them more letters. But it's pretty straightforward, right? And the reason we're going to go over this code is because one, it uses a lot of the concepts we just learned in this lesson, and two, some of your homework is going to be based on this, so it's going to be useful for you to look at this and understand it. Is everyone able to take a look at that? And yeah, once you have that saved, you can commit base, and you can, since it's a generator, you just run it like this with some text. Oh, sorry. You need to pass it some text and a number for how many letters you want to shift it by. So, and there you have it. So that's what it's doing, right? You can give it a different number and it'll encode your text with a different shift. So Neil, we're about to hit 10:30. I was hoping to have a little more time to go through this, but it looks like we are going to be short on time. What do you think we should do?
Okay. The points that we really want to draw out of this code for you. This is probably the most complicated piece of Hoon code that you've looked at so far. The mitigating factor is that it's pretty well organized, except that you have to keep track of all these different arms. So what we would like you to do, the homework will have you modify this program in a couple of ways. So you'll need to understand how it works when you work through it piece by piece. The parts of it that are probably going to be most surprising to you looking at this. The first is line 2. There's a tisgal that composes two expressions in reversed order. It just lets us change which Hoon expression is evaluated next. It has two daughter expressions. The first daughter expression consists of lines 3 through 5. The second daughter expression is the bar send starting on line 7. It's the core. So what this does is it defines a core that has all of these arms in it, and then it evaluates the code on lines 3 to 5 using the names that are defined in that core. So everything that you need to interpret what is happening, so CAS lowercase is a tape. So you receive a tape, you receive a number of shifts left and right, and it's going to lowercase the tape, and then it's going to shift it left, and it's going to shift it right in the alphabet. So that's the two parts that it's going to do. Everything else is you going and look at shift and unshift to do basically the same thing, except they use encoder and decoder, so they shift opposite ways. Probably the most complicated part is it builds a map. I guess that's what rotation does here.
Yeah, so
The rotation is a tape and then it builds a map out of that, doesn't it?
yeah, so something kind of how this works is so we have this encoder function, and basically what this is doing is it's gonna build a map from like A to B. So if you're shifting things by one step, it's gonna build a map where the key is A and the value is B, and then the key is B and the value is C, and so on. And that's what this encoder function is doing. Um, and then it's going to be calling these arms down here. So it's going to call space adder, and that's calling map maker, which is really kind of the meat of this thing. So basically, yeah, so kind of the meat of this is building that map between letters like A and B or A and C, whatever. And then once you have that, you call operate and you give it your message and you give it this map that you constructed. And then all operate does, it's just going to turn your message with changing each character using the map. So once you have that map, it's actually, the code is actually pretty straightforward. But the harder part is you're giving this steps as an input, and then you need to build this map from the alphabet to like a shifted alphabet. That's the part that's a little trickier to go through. So yeah. What does that mean, Rashid?
Is that good or bad?
Yeah, this is a big chunk of Hoon code, but yes, but like once you guys are able to read something like this and follow all the steps and understand what's going on, then you'll be much more experienced in like, oh, let me look at this app, like let me figure out how things are working together in this app, figure out what's going on. You'll be able to read like other people's code and like start understanding it like real life code. So this is great practice.
Don't be shy about dropping in the gather
Yeah,
house.
absolutely. I will be like, office hours are for stuff like this. If you get stuck on understanding this, like I'll definitely be there, or just drop your question in the Hooniverse and so on. So yeah, I think we're just about out of time. All right, so I guess I should stop sharing.